In this video, we'll talk about the derivative of the natural log function. So one of the main ways we can use our generic idea for derivatives of inverse functions is with the natural log, because the inverse of the natural log is e to the x, which has a really nice derivative. So we know that if I take f of x being e to the x, then f prime of x is also e to the x, which is nice. And the most important part for our argument here, the inverse function is the natural log of x. Because these are inverses, right? If I compose them together, I get the identity, I get x back. That's our inverse function. So what does our formula tell us? Well, our formula tells us that the derivative of f inverse at some point b is going to be 1 over f prime at f inverse of b. So 1 over f prime of f inverse of b. F inverse of b is just log of b. This is 1 over f prime at log of b. I can then plug log of b into my f prime, which is also e to the x. This is 1 over e to the log of b. Well, e to the log of b is just b because they're inverse functions. This is 1 over b. So going from here to here, and knowing that this was actually the derivative of log at b, means that this tells me that the derivative of log of x is 1 over x, just substituting b's in for x's. We also could have done this more directly, just by saying that if we know that y is the log of x, this means that x equals e to the y. I can then apply derivative to both sides, getting me that 1 equals e to the y times y prime. Divide through, y prime is 1 over e to the y, but e to the y is x, so this is just 1 over x. And I get the same answer that way as well. Our general formula also gives us the same result. So this gives us the one thing we didn't have yet. We did not have a power rule that got us to 1 over x, right? If it was 1 over x, it should be x to the 0 because I'm subtracting 1 from the power. But x to 0 is a constant that just goes to 0. So we did not have any functions yet whose derivative was 1 over x. This gives us a way to get to that function. It also lets us do a lot more complicated derivatives using the chain rule and things like that involving logarithm functions. As an example, I want to find the derivative of log of 4x cubed plus 3x plus 1. This here is a chain rule because I have an outside function of log and an inside function of this polynomial. So if I let u be 4x cubed plus 3x plus 1, the derivative of log of 4x cubed plus 3x plus 1, log goes to 1 over x, so log of something goes to 1 over that thing. 1 over 4x cubed plus 3x plus 1, and then times the derivative of the inside by the chain rule gives me a 12x squared plus 3. Or writing it as a single fraction, my derivative is 12x squared plus 3 divided by 4x cubed plus 3x plus 1. And that's like we can use these inverse function rules to find the derivative formula for the logarithm, which is really nice and give us a power that we didn't have before with 1 over x. And also we can use that with the chain rule to find more complicated derivatives like this one here, where it's just 1 over whatever's inside the log and then times the derivative of the inside.